Again, my name is Karim. I'm a teacher on the subject earthquake engineering. Today we have a lesson 1. We are also the master students. So now we are going to start my course for today. Do you have any idea or have you heard about it? What is earthquake engineering? In your previous study or anywhere? No idea, yes? Okay. If you have no idea, we will discuss it maybe today. I hope you have any ideas or some initial knowledge about what is the earthquake engineering. So we think that the buildings, any historical objects or new buildings, anything which you know is we know that it is something like a statical object, but actually our buildings always in the movement. Okay, so as you know, Uzbekistan is located in some seismic active zones, especially some cities, something like a Tashkent or Samarkand, Bukhara, or especially just the most population regions, just most populated regions, something like a Fergana region, yes, Fergana Valley regions, and Namangan or Andijan is located in most seismic active zones. So that's the reason for just seismic activity, and it's very important for designing the buildings, okay, or some protection of historical buildings from seismic activity. This is a very important thing for our country, okay? So, as you see, here we have a single degree of freedom system. We will think that any building, any type of building, something like this, or like that, you know, so has some its own mass and some spring coefficients and some damping coefficients. Do you know what is damping? Damping. Damping is something like a shock absorber, which helps to prevent building from the high oscillation. Okay. For instance, a simple one of the examples of the damper is the shock absorber of the car. I think everyone knows what is a shock absorber. Shock absorber is if you look at the car, if you drive the car, there is a special equipment which is called the cylinder. Inside the full with oil, it is called it, or gas, it's called shock absorber. In Russian we will call it the amortizator. You know what is the amortizator of car? Maşinanın amortizator var ki, o şanın sağlığı shock absorber'da götürdüğü vesile var. That's the reason for any building has its own damping property, its own stiffness property, and it has its own mass. Okay. Today we are going to discuss about what is the mass, what is the K, spring constant, and movement of the building, and what is the acceleration, what is the speed, what is the displacement. Everything we are going to discuss for today. Okay. I hope it will be easy for you. I hope so. And anyway, we have to learn about what is the acceleration, deceleration. Yesterday, some of your colleagues just asked me what is acceleration, what is deceleration. Yes. Today we will discuss about these topics. Okay. You were just in a hurry yesterday. Okay. I think everybody knows what is the Newton's second law. Yes. What is the Newton's first law? Do you have an idea? No? Yes? No? Yes? You didn't come from the Mars? Or you didn't come from the moon, yeah? You already studied in your school? Yes? Some physical laws, Newton's first law, second law, third law. Newton's first law is about the inertia. Every object can keep its own inertia if you do not influenced with external forces, okay? This is the first law of the Newton. The second law of the law of the Newton is about force which is acting to our body is directly proportional to acceleration and inverse proportional to its own mass. Okay? It means that if you are acting to any object with some force, something like this, it is directly proportional its own acceleration, inverse proportional its own mass. Okay? If I didn't make any mistake, maybe inverse. Another principle, the D'Alembert's principle, is system supposed in dynamic equilibrium. The principle static and applied by introducing frictional inertia force, everything product of mass and time, its acceleration acting in a direction opposite to the acceleration. It means that if you are acting your system in this way, the system acts in opposite way with some inertia or frictional forces, anything, the acting direction, okay? It's something like, we call it Newton's third law, yes? Yesterday we discussed about some reaction forces and external forces. If we have imagine that external forces which I am acting to my building, the reaction forces will be the inverse force of your building, okay? If I am moving like this, reaction force backward or building, okay? You understand? This is a called D'Alembert principle, okay? In this formulation or in this sample, as you see, we have some spring constant and we have some mass. This is ut, means is a displacement of the time, okay? And pt is the external force, okay? The unit of k is equal to Newton per meter, okay? If you have a higher displacement, the force also will be higher. So this constant will be the same for the some spring, okay? If we have a linearity, if non-linearity occurs, so it will also change, okay? This is a type of linearity and non-linearity principle. Maybe you have already done in your material science courses. If you have studied in bachelor degree, some material science courses, and so on and so on. Have you ever seen that tension testing machine? If we have bar, we will try to make a tension, and then after some time, it will become non-returnable. This is plastic region and elastic region. If we finish the elastic region, it will becomes a plastic. Okay, that's why in this case, for any steel or any material, plastic region starts. So it means that spring coefficient is going to change. Okay, so let's start from spring. What is spring? You know, it is not a spring which you understand. Like after the winter, it's not like a season. It is another thing. Spring in Russian we will call it prужина. Yes. It has its own coefficient k. So spring force is equal to F is equal to k product something like a ut. Okay. Ut in our case is displacement. K is a spring coefficient. Any force which we can measure from the spring, it is directly proportional to the displacement, okay? If we are in the region of elasticity, if elasticity region finishes, so spring coefficient is also going to change, okay? Do you know this kind of thing? In your material science, if you remember, we tested some materials. This is a sigma. This is a, I don't know, maybe this is a sigma. This is sigma. And this one is equal to S. Let me say S, elongation. Okay? Or let me say L. L is better. elongation. This is a if we have any material, steel, bar, anything like a ferrite material, if we try to tension this material, we have such a limit. This is called elastic limit, elastic region. After elastic region, we have a plastic region. Our spring goes to plastic region, and the characteristic of spring is going to change. Okay. For the building is also the same. Okay. For the building is also the same. Building has a spring like this, not like this, but we have something like a torsional spring. After acting some forces, okay, never mind. I can break it, it never returns. Okay? This is called the border of the elastic region. Okay? After that, we have a plastic region. It becomes a plastic. Okay, this is not a bad thing. We can glue it, and we will reconstruct it for the next lessons. So any spring has a plastic and elastic region. Okay, let's take something like this bar. If we have something like this bar, if I tighten this, it will return. Okay, its own initial position. This is a called spring coefficient. This force is returning back. This is spring force. Okay, I am acting with my finger and returning it back. It's something like this. The force is the external force. Okay, it has some mass. It has some coefficient, and then our object is going to move something like this with its own mass and its own spring coefficient, and it has its own some natural frequency, damping factor, and so on and so on. Any building has the same characteristics. Okay, if you harden the building with very high, tough concrete, okay, something like a ultra strength concrete, I don't know, UFDC or UDFC, I don't know the exact name of this concrete. There is such kind of concrete exists which is used. UHPC. Yeah, yes, UHPC. Such kind of concrete exist, which is very hard, but anyway, it has also its own spring coefficients, and it has its own some mass, and they are also not a very hard object. They are also elastic and plastic properties exist. Okay. So, and here we have Newton's second law. We explained it. Mass and product is this double dot means is the acceleration. Okay. U dot is U is the displacement. UT is displacement. U dot T is velocity. And U dot T is acceleration. Okay? Do you have any idea about what is acceleration, what is the displacement, what is velocity? Today we are going to discuss about what is acceleration, what is velocity, and what is displacement, and so on. Okay? Please move a little bit if possible. We have not enough space. We already prepared for 6 people. Anyway, no more than 6 people are going to arrive to our lesson. Okay? So, to our object acting different type of forces. Yes, from the Newton's second law. First one is MUT. Mu dot T is mass and its own acceleration, and force of inertia. Okay, inertial force of our object. Second one is PT, is the external force. Okay, and the third one is the force of spring. Okay, we have such a condition. All our object will be in equilibrium. All these external forces and internal forces of our object will be equal in condition, in equal condition. This is called the equilibrium condition. Okay. If I tighten this spring, it is returning back, yes? It means that it's coming like this, and it's in static condition, so it means that it's coming to in equilibrium position, okay? You understand? If these forces are different from each other, so it is going to move somewhere like this, and so on, okay? If they are in action, it means that they are not in the equilibrium, okay? So, here is our formulation. Let me clean up. Forces which is acting to our object, okay? This is something like external force, it's all inertia, and this is a spring force, or stiffness of our object, okay? So, if we try to identify our body and try to equalize into in dynamic equilibrium in our case, so if we derive everything in one side, okay, if I move this one here and this one here, our formulation will become something like this. Pt is equal to, Pt minus Kut minus Nu double dot is equal to 0. Okay? This is called the dynamic equilibrium. Okay? This condition is called dynamic equilibrium. Our object will be in dynamic equilibrium when we have all these external forces, all internal forces of our object. If we subtract and if we add everything, is equal to 0. This is called equilibrium condition. The condition is that when I move it, something like this, please look. This, yes, it is becoming the middle point. It is in 1 second, in any second, it's stopping and there is no movement. This is condition called equilibrium condition, okay? All forces just neglecting each other, okay? Okay. So now we are just looking only single degree of freedom. We have multi-degree of freedom also exists. We will discuss about multi-degree of freedom later, okay? So let me, if possible, take some object from here. This is okay for some examples.
Are you going to destroy everything here?
Yes, I made myself. For previous master students. This type of thing is called something like, let me say, multi-degree of freedom, because we have 1, 2, 3, 4, 5, 6 maybe floors with this ground, maybe 7 floors. That's why 7 we have different mass, different stiffness, different floors. This is something like a multi-degree of freedom system, okay? Multiple input and multiple output will occur in each floor, okay? We, most of the cases in our wall or in our region, we will use like a multi-degree of freedom. Single cases is easy to understand for the showing students and other stuff. And what is a spring and what is a spring coefficient, everything we will discuss about right now. Spring force, such kind of a force, if you put it in like this, in parallel case, something like this, so two spring forces is going to add to each other, okay? This is a simple physics from the school, yes? If you have two spring, if you put them in parallel case, so stiffness of the springs is going to add it to each other. Okay? Parallel case is not so difficult. But if we put spring in serial cases, first spring and putting another spring, so in these cases, a little bit difficultly it is going to add to each other. Okay? As you see, we have something like this force F1, F2 for different type of springs. And that's why statically it's going to equal to 1K is the final spring coefficient of our object. And then this is K is equal to something like, I don't know, it could be any K. Okay? That's why we can derive this K using like this formulation. Okay? This is called inversely proportional to each other. Okay? Not directly proportional. This is inversely proportional to each other. This springs. Okay? Let me show some examples, if possible. If I have the ability to show you something like this springs. Okay? And here, for instance, we have different type of two springs. Can you or not? Maybe we have the ability to add to each other two springs. Okay, if we have any glue, maybe I can do it. But I don't have any glue, that's right, I cannot do it. If I have a parallel case, it will be like something like this. Okay? You understand? If we have a serial cases, it will be something like this. If I have a serial cases, the final spring stiffness is going to change. It will be different. For instance, this is a hard. Maybe this is more harder. If I put it in longer case, maybe in this case it's not any more harder. Okay, it could be something like a soft and so on and so on. Okay, you understand? Or not so? I have no glue. If I have any glue, I can show you this one. Okay, never mind. If you do not understand, just please accept it. Okay? So in first case, we have a two spring, one mass in it. Yes. In first case, we have what? This is a wall, like yesterday. This is K1, this is K2. Both of them connected in single mass. Yeah, you can do something like this. Mass has some wheels. If I try to move this one, this ball spring is going to, how can I say it? Against to my movement. Okay? That's why I have to add this both spring coefficient like a 2 force. Here is the force 1, here is the force 2 is acting in both cases. If I have an external force, these two forces are going to add. Okay? You understand? For the external, you want to find the external force. Okay? That's why K, final K, you can say, is equal to K1 plus K2 itself. Okay? In the second case, I have a little bit different condition. This is the first case. This is the second case. In the second case, I have put one spring like this, second spring like this. I have a mass. K1, K2. It is something like a, what kind of, it looks like this thing? It is looks like something like a, what can I say? If one combine can assemble the wick in half an hour. The second combine can assemble the wick in an hour. Okay? You have two machines. One machine can finish the job in 1 hour. Second machine, the finish job in half an hour. Okay, maybe 30 minutes. So how much time do we need for if we use both machines to finish one object, the same object? Okay? Do you understand? Or not? So I have a one object. I can finish this object, for instance, in 30 minutes. With machine one. The same object, I can do it with the second new machine that I have in 16 minutes. Yes? Yes? This is a mathematical problem, if you remember. When you are students in the bachelor degree or if you finish the school, there was some problem, something like this. Yes? And how much time do I need to finish this the same job if I use both machines? M1 and M2 together. Yes? It is not going to add directly something like this. If I add this one and this one, how much time do I need? In this case? 90 minutes, yeah? Do you think it's logically true? So why I need, if I have 19 minutes to make some job, two machines. In this case, maybe better to use second machine or the first machine. You can do it in half an hour, or this one can do it in 60 minutes. So, in this case, you cannot add directly, okay? This is called inverse proportionality, okay? So, for doing one job for both machines, how much time do I need? This is called, for instance, for this one is time 1. For this one is time 2. Final time for me is needed for finishing this job. This will be equal to time 1 plus 1 hour time 2. If you calculate this one, you can find final time. This will be less than this one and less than this one. Okay? Maybe 20 minutes, I don't know. Let's calculate. If we have a calculator, 1 over TF will be equal to T2 plus T1 over T1 T2. So TF will be equal to T1 over T2 divided by T1 plus T2. Please calculate if you have some calculator. You can derive how much time do we need. It's easy. Spring in series also the same like this problem. Okay? Did you understand what I'm saying? Yes? Why you are smiling? What are you saying? Yes, something like that. I have never, ever, forever understood this one. Okay, you have a calculator? Please calculate. So 30 plus 60 divided by 90. So 20 minutes. Yes? TF in our case, 20 minutes. This is just a sample. Okay? This is just a sample. This is how to show you what is the inverse proportionality. Okay? Did you understand? If I have one hard spring and if I have another hard spring, if I connect this both spring in series, yes, the final spring will be not anymore hard. This will be a little bit looser. Okay? That's the reason for this is inverse proportional to each other. If you solve this way, in this case, final coefficient, this spring stiffness will become something like this, like a time, like this one. Okay? Logically, it's something like this. Okay? Can I clean this? Yep. Okay. Just a moment. I will write for the spring. Final K is let me write KF is equal to 1 over K1 plus 1 over K2. Okay? In this case, KF will be equal to K1 over K2 divided by K1 plus K2. This is for the second case, okay? Okay, this one for the second case, this one is for the first case. Okay, you can take the photo and you can see what is the inverse proportionality, what is the direct proportionality. In both cases, the force are the same. Here we added the force. This way, final force will be equal to K product something else. Okay? From this side, maybe very small displacement. From this side, also very small displacement. But we have a final displacement, addition of both this displacement. Okay? That's why the final force will be equal to inverse proportionality of both spring coefficients, stiffness. Sorry. Okay? So next. So what kind of degree do we have in a statistic frame? I think you already know about what is the degree of freedom. Yesterday also we discussed it. Yes? And in statistic frame has a 6 active degree of freedom. Yes? Am I right? So X, Y, Z, it's a gravitational motion. Every object in the space we have a 6 degree of freedom. If we look some axial deformation, if we remove them, so we have some only 3 degree of freedom is remains. If you look in 2D case, so we can have only 3 degree of freedom remains. 1 rotation and 2 just moving case, X and Y direction. Okay, you understand? And only 1 degree of freedom left. Frame consisting in heavy roof supported by light columns. Okay? If this is not so hard, here we have a 3 degree of freedom. But in this case, we see that this object is rigid. Okay? There is no any elasticity or some plasticity. It's why it's very rigid and hard object. Rigid means it's very hard. You cannot make a buckling or you cannot deflect the object. Okay? This is called a rigid body. Okay? In this case, stiffness of this one will be equal to K is equal to 24 times Young modulus product inertial mass. Inertia, I think. Inertial mass. This is inertia divided by the length of the spring screw. Okay? This is called spring stiffness. For column spring, like this one, we have something like this, always, okay? If you have different section, rectangular, circular, or circular with a full, and maybe quadratic, maybe triangular, this stiffness is going to change. Why? Because the inertia will be different for different objects, okay? This moment of inertia is going to change, okay? Please write this one also. Can I bring this one? Что надо? Что я слушаю? Надо знать. А? Mega space? I think we have not enough time to finish this course till the end. Because this course is not for 6 credit subject. Anyway, you have a 6 credit, but for the 6 credit you need to have at least 19 hours. 19 hours lesson. But actually, last year we had 16 hours. now it is 54 hours. The course was about 15 weeks totally, 15. They cut it into 9 weeks, and from 9 weeks now we have 54 hours. I can have a lesson. Before this one is about 90 hours, but in 90 hours also we didn't finish. It's a half of this course. This is a very big course. It's about maybe 180 hours. We have to study 2 semesters, but we are not civil engineering students. That's why maybe we will have one sort of this course, okay? It's not my fault, or administration just requesting from us to cut. Maybe finally you have a course will be something like I will going to show only content, or like this, blah, blah, blah. Okay, you can go. And here is your diploma, and you can leave it. Okay? Maybe next year, after 3 years, I don't know. I hope so. The course will be something like this. I don't know why they are cutting this, but this is very important. Maybe not so important for you, but this is also important some part. For civil engineering students, it's very, very important. Okay, very, very important. Okay, good. So we have the K is equal to from both sides 24. What? You lose something? E, I, and L cubed. L is the length. And E, Young models. This should be momentum of inertia. I don't remember exact name. Maybe in the next slide it should be inertia. Momentum of inertia. Should be momentum of inertia. For any section, it's going to change. Okay? Yes. I and J, actually they are the same. So, they made a mistake. It should be moment of inertia. It is horrible, terrible. Next slides. Please close your eyes. If you do something like a surprise. So in our case, we have some mass and spring coefficient. K is equal to here, something like this. And some forces is going to act over it, okay? This is our single degree of freedom system, okay? I showed you my previous slides, something like this. This is a very, very simple case, okay? Instead of this one, we have something like a very long stick. It's going to keep it, our object, okay? We will think that this one has no any mass, okay? If it has some mass, it will be also, it should be also calculated. Now we will think it has no any mass, okay? And next one, this type of system, this is a little bit different in our previous cases. Okay, you can have a photo later, or I have already camera. Maybe everything is okay. I can send it to your group. I can upload to some YouTube channels. Okay, maybe this is better. Because Telegram cannot accept more than 4 GB file if you are not a premium user. I have no such kind of money for the Telegram. I send for you just 4 GB video. I think. For anyone who did not come to our lesson, they have if they have no time to come in lesson, they have 2 times no time to see such kind of video. I think if they have time, they will come here and they will try to listen to this lesson themselves. If they have no time to come to the lesson, it means that they have twice no time to see this video. They will try to open Instagram, YouTube, blah 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 blah, or video, something like this. It's something like a radio, okay? My all voices, every my lesson, okay? I think if you come here, if you try to learn here, it's better to ask from the teacher yourself. If you go to your home, if you want to see some videos, you will never understand. You will never understand. If you are first time coming here, you will never ever, forever understand everything, okay? It's very difficult. Menga bunaqa yomon qaramang. Yoqib aytgan bo'lsa ketavering. Darsga kelmasangiz umuman tushunmaysiz deyapman. Darsga kelmasangiz umuman tushunmaysiz. Hozir videoga olyapman, videoni lekin tashlab beraman. Videoni ko'rayotgan odamlar uyda o'tirib tushunaman deb umuman o'ylamasin deyapman. Bu qiyin masala. Chunki meni o'zimdan ololmagan odam videodan umuman olmaydi-da. Alo. Assalomu alaykum. Ha, domla dastur. Men darsni 8dan keyin tugaganman. 8dan keyin tugadim. 8dan keyin tugadi, 8dan keyin. Bundan kesin o'qigan narsa bo'lib, men boraman o'qigan narsa. Uni berib yubordim, ichida bormi emas? Ya o'g'lan da bor, buxgalteriyada bo'lish kerak. Akmalakalardan so'rab ko'rish kerak, sho'rda boramiz. Sorry. This is another case. This is a disc in rotation with a heavy mass. Okay. We have another spring. This is not only spring like before. This was our first spring. In the second case, we have a spring, but this is a torsional spring. Okay. This is not like this. This is like this. Okay. I'm rotating like this, and it's moving back. Okay. Have you ever tried like this? It's returning back its own initial position. Yes. One of the example of torsional spring is a car baggage. Mashinani bagaj borku, o'sha torsional springdan misol. Bagajni mashinaning orqasida bitta prujina mana turadi. Bu prujinadan bagajni ko'tarib beradi. O'sha torsional spring, dualishga ishlaydi. Tushunadingmi? Torsional prujina, bu holatda bu tushunadi. In this case also we have a torsional spring cases. So we have a rotation motion. This is very heavy disc. So you can see that why we need any heavy disc. But if you look the building, okay, I was doing this very tall building for you. I hope I can't break this one. Yeah. Yes. If you look this object, if I try to rotate this one, you see that? This is a called torsional motion. Okay? This is the same case. Okay? I am trying to force it like this. It's going to return its own initial position. Let's try to return initial position. This is called the torsional motion. Okay? Torsional motion, the torsional spring positions. Okay? In this case, in the previous case, we had what? Let's see. There was a mass, spring, and some displacement. Yeah, this was a displacement. Our initial thing in this case is displacement. In the second case, it is not a displacement; it is an angle. Angle. Okay. What is? Do you know what is angle? Huh? What's angle? What mother does? In the second case, we have an angle of rotation. It's important because if I have a distance bigger, for instance, distance could be changed. here smaller distance, maybe the same change. Okay? It is not depend on distance anymore here. Yes? It is depend on angle. Okay? Angle of rotation. You understand? This is a sigma. Sigma mı? Theta mı yapıyor? I don't remember this Greek alphabet. Eta. Yes? Theta. Okay, this is a theta. You're lucky. This is a called theta. This theta, here we have a angular movement, angle, this is a theta, and we have angular speed, which is a theta dot, and we have angular acceleration. Theta double dot is angular acceleration. Instead of mass, here we had a mass, we have here very big heavy object. Okay? This is a called J. J is the moment of inertia. Moment of inertia. Okay? You know what is a moment of inertia? No, this is a, in this case, this is not a mass. This is a called moment of inertia, okay? I'm drawing very ideal circle, but your eyes maybe cannot see it. Okay? So moment of inertia will be different for different objects. One of the sample of moment of inertia is a simple disk. If the same mass has the same disk, which we have something like this, with the holes and without hole, which one has a more moment of inertia? Here the mass is the same, m1. Here is also m1. The diameter also is the same, d1. This one also d1. But here we have a small diameter, d. But all mass is located in the, not in the same way. It is located in some corners of our disk. Okay, outside places of our disk. Maybe this has a more density. This one has a lower density. That's why the same disk, the same thing, but this both disk has different moment of inertia. Okay. This disk has a J. Let me say J1. This one has a J2. In this case, J1 will be bigger than J2. Okay. If we put both this type of object in inclined plane, let me show you something like this. Inclined plane, like this, like this. If I put both of them here like this, I will put them for the specially something like for gravity like this. Now they are almost the same for both cases. That's why they run in the same speed. Okay. If you have a higher moment of inertia like this and lower here moment of inertia, this disk goes slowly. Okay. This disk goes faster, even if they have the same diameter. Okay? Did you understand? This kind of things is called moment of inertia. This is maybe not so famous in our Earth, but if you go to space, this is very important. If you go to USSR, some I don't know, International Space Station, if you have very big moment of inertia, you cannot rotate yourself. Okay? This is very important. I can show you some examples maybe later. I can show you some videos for understanding what is the moment of inertia. Okay, maybe we have enough time for showing this video. Anyway, 3 pages doing nothing. It's better showing some video, yes? This one. here.
On this incline, and the one with the greater rotational inertia will lose the race because it will have greater resistance to a change in the state of rotational motion. Now, right now, the state of rotational motion of both objects is zero. They're not rotating.
Okay, I want to show you this video, but unfortunately, maybe this is okay for the.
On this incline, and the one with the greater rotational inertia
Is it visible for everyone?
lose the race because it will have a greater resistance to a change in the state of rotational motion.
Look at this
Now, right
both
now,
object.
the rotational motion
They have the same diameter, the same mass,
Once I remove
but one is made from steel, second one made from the wood.
quickly, let's see which
Look
one
at
that
the
is.
moment of inertia of both objects. Did you see that? Wood goes faster because inertia of wood is smaller.
And the one with the greater
Moment of inertia, I'm sorry, not inertia, moment of
will lose the
inertia.
race.
They have the same mass because massасы bir xil, только bittasi zisiga katta, chetda joylashgan diametrda, ikkinchisi anaqa. Bir xil распределенный massa turibdi.
One of them is going to rotate quickly. Let's see which one that is.
Do you see that? This is a called moment of inertia
On
of
this
object.
incline. And the one with the greater
Okay,
rotational
thank you very
inertia
much.
will lose the
It's okay? I can see it. Ah, yes. Already done. So, as you see, we have such kind of thing is called moment of inertia of object. Okay? If we have more denser mass is outside the object disk, it means that it has a more inertia. Okay? If this is a separated whole the disk body, it has the same something. It has a smaller moment of inertia. Did you understand this principle right now? What is the inertia of moment? Inertia is something like a mass, but it is not a mass. Because in that case, in that video, if you saw that, the mass was the same, but they have a different type of speed, different type of acceleration, yes? That's why it is not a mass. It is okay for rotational motion, okay? Moment of inertia. If you look something like this case, if you have the same this like this, in this case, everything will be the same, okay? If you have rotational motion, so principle is going to change, okay? It's different, okay? You understand? Okay. So, in this case, of course, we have some movement. This is theta, is the rotation, r is the radius, m is the mass of object, g should be gravity center. If I didn't make a mistake, it should be gravity center. In moment of inertia, the important thing is the gravity center. Where is our gravity center is located? This is important. For the building also, gravity center is very important. Mass center, center of mass. Center of mass is important. If you are shaking your building, center of mass is not located in the middle side. If you are shaking with both axes, it is going to rotate something like this in XY axis. Okay? Because center of mass will be in different point. That's why it is going to give you some rotational motion. Okay? That's the reason for G is also very important. Okay? So for the case of the disk, moment of inertia is equal to mr squared divided by 2. Okay? For the case of disk. If we have something like this, like a punch, what do you call it? This one. Do not, yeah. Do not. Something like a do not. This will be not like this. This will be, of course, higher than this one. I don't know exactly what was the number, but it is exactly higher than this one. Because the density of the mass basically separated in the another outside of our circle. Okay? You got it? Okay. Let's have a break a little bit and we can continue after the break, okay? Our subject.
Там еще обычно, когда говорят про линейную инерцию, хороший пример это когда фигуристки